In this video, you're going to see the signature or device ID read out of an AVR microcontroller by hand. You'll hear some about AVR device signatures, what they are, why you might want to read one, and see one actually read using this setup with switches and lights. This video is part of a series, so you may be a little lost if you haven't seen the previous one that explains what's on this board and how it's operated. If you've been following along from the previous video, you'll understand what I'm about to do as entering the programming enable instruction. In the previous video, I'd mentioned that this chip can be brought up into the reset state. By powering the chip into the reset state, you can get into the programming interface before the chip has any opportunity to run any code. Imagine, for example, that you wanted to be able to read the EEPROM out of the chip before any code could run that could change the content of the EEPROM. Just for a little bit of variety, I'm going to show you what it's like powering the chip up into reset. So I've set the reset switch low. I'm setting my clock line low because that's a requirement for the programming enable command. And then I'm going to power cycle the board. When I cut power of the board, you'll see this meter go out. Alright, now you'll see the meter come back on as I plug it in again. So we've powered the board up with reset low and with the clock line low. So we're now ready to enter the programming enable instruction. So now the chip is ready to receive other programming instructions. From the moment of reset, the chip is effectively counting bits going into it. All of the instructions are 32 bits long, and they're entered consecutively. So they're all perfectly aligned on 32-bit boundaries, and the first one has to be that programming enable instruction. If I were to set this switch high and then low again, taking the chip out of reset and putting it back into reset, I would have to re-enter that programming enable instruction. So this is generally not done very often during programming. There are only a couple reasons for leaving the reset state. One reason is just that you're done programming and you want the chip to be able to run code again. In some places in AVR documentation, it says that you have to release reset in order to complete a chip erase command. But that doesn't appear to be the case generally. I'll probably say more about that when doing a chip erase. Changes to the configuration fuses only become effective when leaving reset. So if you were to enter a write fuse instruction to switch system clock sources or to enable the clock output feature, it won't actually do that until you release reset. If a programmer doesn't see what it sent come back to it 8 bits later, per the usual echo mechanism, that's probably a good reason to leave reset as well. For me, operating this by hand, sometimes I just screw things up. When that happens, I typically need to leave and re-enter reset so that the instructions I'm entering become correctly aligned on 32-bit boundaries again. All AVR made by Atmel, now Microchip, have a 3-byte code called a signature that more or less identifies the specific AVR part. For the ATtiny13A that's on this board, the signature is 1E9007 in hexadecimal. Any ATtiny13A will have these same exact signature byte values. Every AVR datasheet gives the signature byte values for whatever parts it covers. Not all AVR datasheets make this clear, but there is actually some structure to the signature byte values. The 1E hexadecimal value for the first byte identifies devices manufactured by Atmel, or now Microchip. I'm not aware of any AVR signatures starting with anything other than 1E. So far as I know, they're all manufactured by Atmel or Microchip. The only AVR, or rather AVR compatible chips that I'm aware of are from a company that is or was called Logic Green. I've helped people with them, but I haven't used them myself. I've not been able to confirm that they have their own signatures at all, and they don't seem to use the Atmel AVR ISP protocol in any case. The second signature byte has values that indicate something about how much flash the AVR has. The exact mapping between the second byte's value and how much flash the part has is largely dependent on the series it belongs to, and there are also some exceptions. It's really kind of a mess now, but if you're curious, I put this chart together that covers most of the AVR parts. Here's the 90 hex value indicating the ATtiny13A's 1 kilobyte of flash. The third byte makes the signature unique among those AVR made by Atmel that have the same amount of flash. If there's any meaning to the third byte's value beyond its uniqueness, I don't know what it is. Here are a couple of Digispark clones, one that's made more or less like the original Digispark, and another that's been made with through-hole components. They both use ATtiny85 parts. Both have the same signature. It doesn't matter that one of them is in a through-hole DIP package and the other one is in a surface mount SOIC package. The package type factors into the ordering code, which you might call a part number, but so far as Atmel and the signature is concerned, these are the same part. So these are the same chip, they're just in different plastic boxes basically. I said that the signature more or less identifies the part. The ATtiny13A happens to be a good example of what I meant by that. There is an older original ATtiny13 without the A revision mark in the part name. As I understand it, the A revision is basically the same part. The difference is just that the ATtiny13A is made with a newer fabrication process. However, parts made with newer processes that might even be described as having improved electrical characteristics can sometimes behave worse in existing designs. In any case, the signatures are not quite in a one-to-one relationship with part numbers. As you can see, there are a lot of A revision parts sharing signatures with non-A revision ones. Here's a newer B revision of the ATmega 328P that's used in some Arduinos. However, it has added features, such as a second UART, and has a different signature. After the Programming Enable ISP instruction, the next ISP instructions issued are usually for reading the chip's signature. This is done to confirm that the chip is the one that you think it is. Usually you don't want to program a chip with code that hasn't been written for it. Reading the signature also helps validate that the connection is working. Some programmers, like the Arduino ISP Eno sketch, as it's currently written anyway, ignore data coming out of the chip unless it's in response to a request for data such as reading the signature. So they're not even checking to see that part of the Programming Enable instruction was echoed back. Unlike some AVR programmers, the Arduino ISP Eno sketch also doesn't have a mechanism to check for the target voltage. That means that the act of reading the device's signature is the first moment where you could have any idea that there might be a problem with your wiring. The basic process for entering the read signature byte instruction is the same as it is for entering the Programming Enable instruction. However, this time there are two main differences. You may recall from the last video that most of the time the data coming back to us on MISO, the red LED, is the previous byte we sent being fed back to us as a kind of confirmation that the connection is okay. However, when we're asking to read data from the chip, that data is sent to us on MISO during the fourth and final byte of the instruction. So during the fourth byte of the read signature instruction, the chip will send us the signature byte value instead of echoing back the previous byte that we sent to it. Also during the fourth byte, the data that we're sending to the chip is treated as don't care bits. So we can send whatever we like out to the chip during that time. The other difference is that the read signature byte instruction is parameterized for which of the three signature byte values that we're reading. To get all three signature bytes, this instruction has to be entered 3 times. Each time it's issued with a different bit pattern here in the last 2 bits of the third byte. There are only 3 signature bytes. They could have repeated this instruction 3 times in the table, just filling in 3 different bit patterns here and then giving the instructions 3 different names. But they chose not to, at least in the ATtiny13A datasheet. In this form, you can think of it as a function that's named with these bits, and these bits are a parameter. Or you can think of it as being like a machine code instruction where these bits make up what's called the opcode, and these bits form the value of an operand. For comparison, here's an actual AVR machine code instruction, not an ISP instruction. In both cases, there are bits that are just specified as numbers. These identify the basic nature of the instruction, that is, as a read signature byte ISP instruction or a read IO space AVR instruction, for example. The AVR instruction is also parameterized using bit fields labeled with letters. They're using one field to identify the destination register, and they're using a different field to identify the IO space address. When you're using AVR assembly language, an assembler normally stuffs these bit fields in the machine code for you. So we're going to read the first signature byte out of the chip. That's the signature byte at index 0. That means that 0 values are going to go into the B bits. You can send whatever you like for the don't care bits that are marked X, and you can also send whatever you like during the last byte for the bits that are marked O for output from the chip. The typical convention is to send zeros. I will send zeros until the last byte, and then I'll send ones. For me, this is a good compromise between being easy to send and having easy to interpret output on this red LED for the MISO signal. During the last byte, we expect to get back 1E for the first signature byte value. That's 1E hex, or 0001 1110 in binary. And for the rest of the inbound bits, we expect to get the usual echo back of whatever we sent 8 bits ago coming back to us on MISO. The first of these will be the 8 zeros that I just sent as part of the programming enable instruction. Briefly, the process is the same as is outlined in the previous video. We're going to look at the red LED to see if there's any data coming from the chip, if that's relevant. We're going to set the data switch for whatever we want to go into the chip, up for a high and down for a low, and then we're going to pulse the clock up and then down. And that happens for all 32 bits of the instruction. So I'm going to send out the first 3 bytes of the instruction now. I'm going to go fairly slowly so you can confirm on the red LED that we're getting back the expected data. So we should be getting back the first of our 8 signature byte bits now. I'm going to switch the data switch high because I'm going to send out ones for our don't care bits during this last part of the instruction. So we're receiving the first 0 bit, and we should have 2 more 0 bits following that. And we do. And then we should get 4 1 bits. There's 1 of them. 2 of them, 3 of them, 4 of them. And then we should get 1 0 following this. And we do. Now I'm going to toggle this switch up and down to complete the last bit, and when we do, we should see the red LED turn on because we've been sending out 8 don't care bits. And it does. So that's our first signature byte, 1E for a chip made by Atmel. The process of getting the next signature byte will be essentially the same. The difference is that I'll be sending 01 for the B bits. During the last byte of the instruction, I'm going to send zeros out for the don't cares. So we're receiving the first bit of our second signature byte now. That's a 1, because the value is 90 in hexadecimal. So we'll be getting a 1001, and then 4 zeros. There's our 1. There's our first of our zeros. The second 0. The next one should be a 1, and it is. And then we should get 4 zeros. Now I'm just going to pulse the clock up and down one more time to get us aligned on the next instruction. So there's our 90 that marks this chip as being one that has 1 kilobyte of flash. So the process of getting the last signature byte is going to be the same, except we'll be sending in 1 0 or 2 decimal for the B bits, and we'll be getting back a 7, which in binary will be 5 zeros followed by 3 1s. I'm just going to put in the first 3 bytes. Now I'm just going to send our 2 in, so we need a 1 followed by a 0. I'm going to be sending in 1s for our don't cares. We're now receiving the first bit of our last signature byte. So that's our first of 5 zeros. We should get 4 more zeros. And we do. And then we should get 3 1s. And we do. I'm just going to send this up and down one more time to get aligned. So that was our 7 in binary for the last signature byte. So as you can see, we are really communicating with the chip. In the next video, we'll see if we can do some flash operations to program an instruction onto the chip to at least turn on this blue LED here. If you're learning something or being entertained by this stuff, let me know.